comprehensive introduction. Let's see here. I will be talking about time-delay perturbations in dark matter substructure with a couple quick forays and other things. Should I be wearing a microphone or something?
Is the sound okay without the mic?
It's supposed to be recorded, so.
Yeah,
So that's okay?
It's fine.
Okay. Can you hear me okay? All right. Jason's looking confused, but I'm sure it's just me. I'll just move my mouth bigger. Well, first and foremost, I'd like to thank all my collaborators because they help me and inspire me in all things, not just in the research that I'm going to be talking about today. The work I'll be talking about today is has mostly been done with Chuck Keaton, and we're making little forays into new projects with Mike Cullen, James Bullock, and Andrew Zettner, whether he knows it or not. But I don't think he's in the room, so I guess we're okay. So you heard from Tommaso and Phil about slacks. This isn't my talk, but I am just constantly tickled by how successful this has been, and it's sort of I guess amusing that at this point, well, if we'd been having this Beyond the Obvious workshop a few years ago, then this would have been one of the Beyond the Obvious things, and now it's absolutely obvious because having gone into production mode, we have the 100 lenses that Greg and Tommaso referred to, including spectacular oddballs like this. So, and it's great to have things like that in sort of the obvious regime. Of course, lenses come in many shapes and forms. Many are discovered sort of systematically like this. Others, like the Haggle's pipeline that Phil has so expertly designed and tuned, is going to mine the Hubble archive and other archives. But of course, we all find orphan lenses now and again. We all, meaning anybody who stared at data, almost, seems to have found either candidates. I mean, I hear little snippets from lots of people. We find candidates, we find things that are spectacular. Do you publish them? Often not, because either you don't have the right context, or it's not spectacular enough, or it would distract from the thing you're really trying to do. So several people have thought about the possibility of having a wiki page where people can contribute their orphan lenses for general perusal, and so that they don't get lost just to be rediscovered in the far future in our all-sky space-based surveys, whenever those might be. So for now, if you're inspired, drop a line to orphanlenses@gmail, and eventually these will be propagated to a wiki page, and we'll sort of chat about this. If you're curious about it, come talk to me, and I'll tell you who else is involved, whatever. It's not supposed to be anything special, apart from trying to rescue poor little orphan lenses. So, onto the main course, which involves using gravitational lensing for probing dark matter substructure, which is, of course, something we're very interested in as a community, because the substructure has a great deal of discriminating power for lots of cosmological and galaxy evolution questions we're keen on. This is the Via Lactea simulation, a little snippet of it at a moderately appropriate redshift of 0.8. And as we know, it has a great deal of substructure. And not only that, but all the substructure has substructure inside of it. And so we have this cascade of scales that probably goes down to as little as 10 to the minus 6 solar masses, although we don't reach that in simulations yet. And all of it is important for studying the physics of the dark matter and the galaxy evolution. And we need clever ways to probe it. So if we think of it in terms of a matter power spectrum, this is one of those cute plots plotted in millions of light years from Max Tegmark that he has on his webpage, showing the CMB. I guess actually this is density fluctuations, which is related to the matter power spectrum itself. We go from large scales to, relatively speaking, very small scales, which is probed by the Lyman alpha forest, and that has been fairly state-of-the-art. But of course we know that if you sort of tilt that and extend the lines up to the left, there's structure that goes down to absolutely minuscule, frighteningly minuscule scales. And these are probed by different techniques. So the Lyman alpha forest continues to probe down to basically sub-megaparsec, let's say, possibly smaller. Then we have dwarf galaxies, which we generally observe with great fidelity very locally only. And then we have smaller level substructures, which we can probe with gravitational lensing. So just to remind ourselves that it's interesting, even though we're fairly confident in the cold dark matter model as a model to test, and even though Sloan is very competently discovering ever increasing numbers of dwarf galaxies, when the sort of mass function of the dwarf galaxies is measured in what Luz Strugari and his collaborators argue is an appropriate way, the problem when you compare the observed mass function of dwarf galaxies with that expected from the Via Lactea simulation is extreme, to the extent of missing thousands of what should be detectable satellite galaxies in our Milky Way. And of course...
Wait, no, what do you mean? I mean, the black curve there is the data, right? And blue and green are theory, right?
Mm-hmm.
So,
Blue and green are a subset of theory.
Yeah.
And red is
Sorry, the red is theory, straight up.
they're all different theories.
They're all theory, that's true.
Blue and green are two of their theories for which ones survive,
Yes.
which visible.
Which ones are
Right.
at the top?
Yeah.
Yeah.
So what's the problem here?
So,
Nothing.
um,
Find the ones
well-
in between that I agree with.
I agree with that.
okay. This is going to be a recurring thing. This is going to be a recurring thing. What are our expectations, which I think is a very open question, and what can be measured at all, and how do you bring those two together? So, I mean, this is perfect for this kind of workshop because all of those are open ideas. So yes, if you tweak the knobs and you pick some certain subsets of your substructure mass function, you might match up what you observe in terms of the dwarf galaxies. But there's a lot that's going on. I'd rather not belabor this one right now, but okay. But there are many different ways of tweaking how much power and sort of density perturbations you get on small scales, as we know. I guess I realize that people are from a variety of specialties, so I didn't want to just go straight to the time delay perturbation stuff right away. So this is all sort of by and by to refresh our memories and set the context a little bit. So I apologize if it doesn't excite you or thrill you as much as it could, or it does others, but that's cool. So there are ways of addressing what may or may not be the substructure problem by considering ways of changing the power spectrum at small scales. So this could be from not having perfectly cold dark matter, having some flavor of warm dark matter, where the dark matter particle has properties that will repress structure on the more moderate scales or smaller scales. And there are various papers that have explored this, usually semi-analytically, because I guess it's very difficult to do in a real numerical simulation. Something Mike Cullen has explained to me a few times, and I sort of understand it, but not so well that I can defend it. So it seems like there's a lot of work to be done in sort of non-standard cold dark matter actual n-body simulations. So anyways, for picking different masses for the dark matter particle, be them sterile neutrinos or just some posited candidate, you get very different power spectrum behavior on very modest scales. So which is also a function of redshift. So it's a strong function of the particle mass and a strong function of redshift. And that's something that you obviously can't do with the set of dwarf galaxies in our Milky Way galaxy, in our local group. And so there's an attraction to going to gravitational lensing, which lets you look at small structure at a variety of different redshifts. Now, So there's a combination of problems. You want to be able to simulate, calculate your predictions so that you have something to compare against, and it could be your vanilla CDM, or it could be other flavors of cosmogony of dark matter physics. And then there's the question of how you make your measurements and then make the comparisons. So I was very tickled by the talk on higher order moments of weak lensing, which goes down to sort of tens of kiloparsec scales, basically. If you can go within sort of strong lensing systems, you're able to go down to a couple orders of magnitude smaller physical scale. So there's an interesting regime that we're beginning to be able to probe. So I realize I'm just talking preamble all this time. So let's go on to the idea itself that I wanted to tell you about. And so there's a generic lensing ray diagram. I had the graphics people at JPL do this, so I show it at every talk because it costs me a lot.
Can I get a copy?
Yes.
Thank you.
Yes. No, I'm happy to share this with everybody. It's rather nice because it shows the Via Lactea plane in the middle, so it gives sort of a starting point for talks to more general audiences, and it's a real HSD image of the quad there. The point of this, for our purposes, is that there are different path lengths for each one of the images, and so if there's a fluctuation in the intensity of your source, you'll see it at different arrival times when you're making your observations from Hubble or the ground. So that arrival time is, at its most basic level, it's very simple. Depends on the potential of the galaxy where the image forms, and also the relative position of where that image is relative to the center of the galaxy, of the lens, and the cosmological distances. But the main point is that the time delays depend, in effect, directly on what this potential is, whereas the actual image positions depend on the first derivative of this equation, and the relative fluxes, the magnifications, will depend on the second derivative of this equation. And since we see that the time depends in a linear sense on the potential, if you're considering small perturbations because substructure, and you're looking at second derivatives, a very small perturbation could cause perhaps order unity differences from what you'd expect from a smooth model. So that's pretty cool. And that's why flux ratios and flux ratio anomalies have been so interesting. If you go to the middle tier, the first derivative, those could be astrometric perturbations, which are potentially measurable, but they're order 10 to the minus 3 arc seconds. We might be in a position to do it statistically today or soon. It's definitely another cup of tea for the near future or medium future. And then you'll, of course, say, well, what am I talking about if I'm talking about perturbations on the time delays? Since those go linearly, they will not be dramatic, but they have some, but they exist, they're potentially measurable, and they have some very nice properties. So let's start by considering a quick mathematical description of what might happen if you have perturbations in the potential. Okay, so let me skip over this particular slide. It's just the preamble that I was just discussing. So there's our time equation again, our time delay or arrival time equation again. And let's say that in a smooth halo, a smooth galactic halo, we have substructure, and just for the purposes of our education at the moment, let's pretend that each one of the substructure points is a point source. So the potential of each substructure subhalo is described in a very straightforward way. So what we're interested in is the potential perturbation at the position that an image forms. Okay? So the total perturbation that you'll experience under that image will be the sum of the potential perturbations, the contributions from all your substructure that you've chosen to throw into this otherwise smooth halo. All right? So that's the picture. What is cool about this? Thank you. Perfect. What's cool, what's neat, is that because it's a linear correspondence between that arrival time and the potential, you can use the central limit theorem as long as the mean and the variance of each one of these terms, each one of these potential contributions, is a finite number, which is probably a pretty reasonable assumption. And you can test it with realizations, of course, which I'll show you in a moment. But it turns out that if you work through the math, which takes a couple pages of math in shortened form with liberal use of Mathematica, you find that it is very tractable analytically, or with this simple potential description, and you get a variance in the time delay differences that relates in a very straightforward way to some properties in the mass function that you've assumed, or the characteristic mass of substructure, if you will. So,
For point masses, that is true.
I'm sorry?
For point masses, that.
Yeah, that's right.
And if it's
That's right.
then it would be, like, if your arm is phi on top.
Uh-huh.
divided by that. Yeah. Sorry.
No, absolutely. No, this is meant to be pedagogical. I mean, it was for us, and we were impressed that it happened, that it worked out well. But then you want to look at more sophisticated cases, yes. And in fact, when we did our realizations that you'll see in a moment, I won't show everything, but we did realizations for point sources and for truncated isothermal structure in the subhalos, for the subhalos. So, right, it's tractable, well behaved. It's a Gaussian process, basically. So, which is something that the astrometric and flux ratio perturbations are not, because they depend very sensitively on the model that you've assumed for the smooth potential as well. But the main reason is because of the first and second derivative relation between the potential and the properties that you're measuring, the astrometric or the flux magnification perturbations. Sorry. So let's take a quick case and look at a few realizations. We considered a fold and a cusp lens, just something that would be representative of typical geometry of 4-image lenses, and took a mass function that was a differential mass function that's sort of plausible, and a mass range that's fairly comfortable to work with, and some fraction of the total mass tied into substructure. So when you consider the perturbations from a series of realizations with these properties, in the end you find that the dispersion in the time delays looks Gaussian, as we were sort of expecting. Of course, I am fibbing right now, because first we did the simulation, scratched our heads, and then went and derived it. But it all works out. So we find that the perturbations are described by basically a variance in this sense. So what you're seeing, if it's not clear, these are basically the time delays between different image sets in the quad, and the vertical line is what you'd expect from the smooth model, and the full histogram is what you get after doing 10 to the 4 realizations of that substructure. So if you go to your equation, where you expect that the variance, the dispersion in that relation, to go as the fraction of matter in substructure and the characteristic mass, you can play around with different fractions of mass in substructure. You can play around with different characteristic masses and sort of see if your simple equation and your realizations agree. And if they didn't agree, I'm not sure I'd be telling you about it right now. But they do, and extremely well. So if you tweak the F sub s, there's very good agreement, and you can sort of see the qualitative behavior. If you consider different mass ranges for the mass function, or different slopes for the differential mass function of substructure, you basically get what you expect from that simple equation. And finally, there's one other nice property that we sort of expected, but we're so pleasantly surprised to see that it worked very well, which is related to one of the degeneracies that we have to deal with when you're doing gravitational lens modeling, which some people describe as the radial profile degeneracy. It's as descriptive as anything else. But basically, you take your lens, and if you don't have independent constraints for what the mass profile should be, the smooth mass profile, it's an almost unlimited set of density profiles you can assume and still fit the model to within your observations. And each one of those models will give you different time delays as well. So you can see this in, if you look on the left-hand panel, if you assume a smooth power law density profile of something, you get a time delay histogram that looks like so. If you assume it's isothermal, you get the same sort of histogram but shifted, and so on if you take a slightly different slope. So this is a set of time delay histograms for one of the image pairs. There it is for another one of the image pairs. Same behavior, different scale. What we find is if you take the ratio of the time delays, effectively that radial profile degeneracy normalizes out. Now we're with slight differences in the behavior of the histogram from one to the next, and this is something we're looking into a little bit more to see how stable the behavior is for very different image configurations in the lenses, things of that nature. But it's sort of cool. It's one of the basic degeneracies that we have to deal with always, and it might be tractable. The key, of course, is to make sure that you've checked the engine very carefully, and ultimately that you can measure the time delays to sufficient precision. Because if you had very keen eyesight from the back, you would have seen that the time delays that you have to measure things with is at worst a few percent, and presently, if not much better. And presently, time delays are measured to, let's say, about 10%. Now, the hope or the expectation is that if this proves to be as good of a probe of dark matter substructure as we think it is, having looked at this for about a year, it could motivate better designed experiments, or experiments that try and nail the precision of time delays to the levels of precision that they could be used. Because the fact is, 10% precision gets you really far if you're looking at Hubble's constant, or if you're using time delays to measure the smooth structure of lenses. But this is sort of taking it to a slightly different level. So if this is beyond the obvious or not, that's up to you to decide. But it's definitely something that's a little bit in the future. So anyways, it's a list of a few of the things that one has to consider and worry about. And we're considering all of these things. As I just said, the measurements could be a challenge. There are some cases that may or may not exist in nature where the effective substructure could be very obvious, and I'll just sort of describe it graphically. In a 4-image lens, so that there's no theorem for what I'm about to say, as far as I know. If you know of one, please tell me. But empirically speaking, once you have built a generic model for a lens, any way you like to, the arrival time, the order of arrival time of information is determined. So you know that you'll get the first, if there's fluctuation, you'll first see it in your first minimum, then your second minimum, then your first saddle, then your second saddle point in the time delay surface. And that's very well determined, even if you go and play around with your smooth profile for your lens a great deal. So what if you find a lens where you get where the leading image is your second minimum, or something like that? You know, if there's an order reversal along the way. A very natural way to explain that, perhaps not the only way to explain that, but a very natural way to explain that would be that there's enough substructure that it's shifted the time delay surface just enough that you end up getting a slightly different order than what you'd expect from a smooth model.
Wouldn't multiplane lenses do exactly the same?
I'm sorry?
Is that holding true also for multiplane lenses?
For multiplane lenses?
Double
Yeah, possibly. Well, you're describing something that would clearly be special, I think. Maybe I'm not understanding entirely, Marusha. Excuse me. Uh-huh. But you'd probably be able to see know that there's more than that. It's not a simple configuration, a simple lens setup. Yeah. And in any case, that would be more rare than just having one thing lined up. So there's one case. This is for Chris to chuckle at. There's one case that we're based on the paper that exists right now. There is a significant deviation or a significant difference in terms of this arrival time, this arrival order in RxJ 1131. Chris tells me that the time delays available on the web may not be the entire truth, but it's still they're redoing an analysis by looking at their entire data set again. But the point is that if one does see this and believes it, okay. Good error bars are always a good thing, Chris. Remember that. This would be a pretty solid case for substructure for significant substructure in a lens. So, not surprising, this is going to be the departure point to the second part of my talk, which, but I guess I've run out of time. No. All I was going to say. So the summary is things we've been talking about just now. All I was going to say was, apart from developing this idea more, we have two things to do. We need to have a better set of predictions for different interesting cases for substructure, realistic substructure, be them from Via Lactea type simulations or semi-analytically built realizations of substructure for different warm dark matter cases or other things that affect the substructure levels. And we need a very good way of connecting the observations that we can make to those predictions. And that is all work that needs to be done. And because this appeared last night, I'll just pop this up and stop in just one moment. Sort of motivated by the potential of this, a number of us have been playing around with a mission idea that could potentially be dedicated to making very high precision measurements in a very large sample of multiply imaged active galactic nuclei, or quasars, with the primary goal of trying to nail the substructure in dark matter question. And that's a topic of, independently of the fact that I'm out of time, it's a topic for another entire talk. It is on SRPH if you want to take a look, and I'd be very, very happy to talk with anybody about this. So I'll stop there. Thank you. I have to say more about it now?
You can stop.
Well, I can show you a sunset from California. How's that? Come and visit me. I'll tell you all about it. The very short version is, what we thought was, partly because of this way of measuring substructure, potential way of measuring substructure, and because of the power of using microlensing, as Chris and his collaborators have been doing, using microlensing to probe the structure of active galactic nuclei, we thought it would be pretty spectacular if you could build a system that, at high angular resolution and being able to work in the UV, so you can go to short wavelengths that are relevant to the AGN, you could get a set of observations that would, at the same time, give you very high precision time delays, which is interesting, measure microlensing behavior for all of your images in this large sample of lenses at many wavelengths at the same time, so that you can get the microlens behavior as a function of wavelength and time, and perhaps with a slightly coarser cadence, get spectroscopy, so you can build a reverberation map of your lenses as well, of the multiply imaged AGN as well. So, and it, I forget, I don't know if that was 1 or 2 or 3 sentences, but the design is fairly straightforward of getting multi-wavelength observations and spectroscopy of many lenses in a dedicated observatory, and the goals are pretty, I mean, the results would be pretty spectacular in terms of the dark matter questions and precise black hole masses and AGN structure as a function of redshift, depending on what lenses you have available for you or what lenses you choose to observe. So now this is in the spirit of, it's a mission concept. So if you look at the paper, you'll see that the science is all compressed in a page or two, and a lot of it is in the actual sort of engineering choices that one makes to build a mission concept, to build the idea. But it's sort of a point of departure. It's like a catalyst to figure out what you can do if you had a dedicated platform, and sort of motivate like exactly what you would measure to sort of motivate the science some more. Yes.
So how different is it to Snap?
The only thing in common with Snap is that it's in space, and that it would need to have very stable pointing, since we're going for subarc second resolution. But otherwise, the field of view is very small,
Right.
because it's tailored towards targeted observations. I mean, what's motivating this is to observe strong lenses in their environment. So it's comparable to ACS in a sense. We want a small enough field of view that we don't go crazy in real estate with detectors, but large enough that we have lots of other sources in the field to calibrate off of, to do the photometry off of.
Okay, so I can see you don't need the large field of view, but maybe Snap would do all of this for you.
If you could take Snap and commandeer it, the thing is that
Right,
these sourced are scattered all over the sky.
Right.
So Phil could probably tell us better than I offhand how many lensed AGN are there going to, may there be in the area that Snap is going to be monitoring for supernovae or any of these other surveys. And it's not going to be a giant number.
Well, I mean, surely you can't go, 1,000 square degrees has got to be a bit.
Are you going to be monitoring 1,000 square degrees for supernovae? See, that's the thing. You're going to find many lenses, but you're not going to be monitoring them. And you're not going to be monitoring them at the cadence you need.
But, I mean, that's a small modification in the sense that couldn't Snap build up its area at depth by doing lots of observations to get the 1,000 square degrees in many.
Now and again, I make noises about this in the Snap meetings, and it's always, it's non-optimal for the rest of the big survey science.
Presumably this will steer a lot faster.
Yeah.
Because one of the
Yes.
changes, right?
Yeah, this would steer very quickly. It'd be very stable, like it would have to dampen vibrations very quickly, and it would be built so that you can actually get to fairly small solar elongations, so that you can observe many things over much of the year. So I mean, you could take something Snap-like and change your strategy or make some choices, sure. But I mean, one question that I've gotten a fair bit, especially at JPL, has been, well, can you do this with Hubble? And the answer is yes, if you commandeer Hubble for 3 years. You really need to build up a fairly richly sampled light curve for everything, and you need to work in as far in the blue as you can, and you need the high resolution. So I could say, yeah, if you could commandeer Snap for 3 years, sure.
You need high resolution for 1.5 meter mirror or something?
That's
This isn't a mid-X, this is bigger than
it can be a mid-X. I mean, the way that this project was built for the one that's on SRPH right now is based on a proposal that we put in for the strategic missions call that NASA had last year. So it was for a perhaps more ambitious project. We explored like how small you can go. It will not fit under a small Explorer program. because both of the sensitivity, but mostly because of the resolution. Like you can't go smaller than a certain level. So this is 1.5 meters. There are choices to make. You could go smaller, and you could fit it in a Medium Explorer program. When the call comes out, or before the call comes out, we'll be exploring like exactly where you can go. It's not a simple question, right? There's so many trades to do. So,
Ground price with AO?
if you can work in the ultraviolet?
No, do you have to really be in the ultraviolet?
It depends on what your science is. I mean, you like anything, you can decide what's important to you, and you can try to do it. Of course, it would also help to observe things during the daytime. I mean, it depends on which lenses you have. I think
A lot cheaper on its own.
all these questions can be answered with the right sort of set of simulators. I don't mean individuals, I mean programs. And I don't have all those answers right now. I'd like to have the answers, but I don't yet. So you're sort of seeing my research path for the next couple of years on this topic. So there's a lot you could do from the ground if you had dedicated observatories. I mean, if we had a worldwide network of, say, 2-meter class things so that you're fairly sensitive and can beat back a lot of systematics, that'd be pretty spectacular. I would totally support that. I would love to work on that. But it may not be enough to do everything that we would want to do and could do with this kind of a platform. So,
I have a question about your time delay perturbation.
yeah.
So, okay, so flux ratios, there are like a couple classes, right? There are systems that are so anomalous that you can't reproduce them with a smooth model.
Mm-hmm.
And then there are some where they're like consistent with substructure. So in the time delay case, it sort of seems like the ones where the arrival times are reversed are like the extreme cases of time delay perturbation.
Mm-hmm.
So what fraction of your simulations are systems in which the time delay is actually reversed?
Which fraction of the systems that we simulate
So you
actually
have-
show time reversal?
Yeah.
Um,
Rather than
the
just a perturbation.
yeah. So to get a reversal, you have to have a pretty substantial mass fairly close to one of the images. And I think that for the realizations we've done, that hasn't happened. I hope I'm not lying, but I'm pretty sure that that's the case. I mean, because we did look at that at one point before we were even thinking about 1131. And there are two reasons for that. One is I think we didn't go to extremely high masses, and on the other hand, because it's this almost n to the -2 power law, even if you do many realizations, you don't get very many of those very massive substructure subhalos, and so having them appear in the right place is pretty rare. But I think in trying to explain 1131, we sort of pushed things to the limit, and even pushing things to the limit, it was hard or impossible to reproduce.
We could sort of explain it by putting something really massive.
Extremely fine-tuned, though. I mean, hand-placed, just so, and we were finding that as well. But then again, that reversal was not just reversed, but pushed by 10 days, right? So quite substantial. I mean, the number we were playing with. And if the errors are different, the errors are different. So,
So there's crystals of fluxes fine.
I'm sorry?
Flux is fine, then you get like extreme microlenses, so you can make flux work if you have something very massive.
Well, probably 1131 just our error bars.
All right, that might be a good place to end on the sunset.
Let's play next weekend.
Thank you.